Hello, it's Professor Pedrero again. We're going to move on to section 5.5b. So solving systems of, solving our differential equations that are non-homogeneous, but using the method of variation of parameters. So that's going to be our objective for today. And we're going to focus on second order differential equations with constant coefficients. And then we are going to use this technique of variation of parameters, unlike the technique of method of undetermined coefficients that we had from the previous section or the previous lesson. Okay, and to do that, we're going to do a couple of things first, a little bit of review. The first thing that we're going to do is review something called the Wronskian of two functions. So it's our way to determine whether two functions in function space are linearly independent or not. And to do that, we take and create a determinant by taking the function, the next function, and if there were a third function, we put him here. Okay, and keep going. But then we're going to, since this is a determinant, we need a square matrix. So we will take the derivatives of those guys. Okay, and then check to see if that determinant is not identically equal to 0. If the determinant is not identically equal to 0, then as a quick reminder, those functions are linearly independent. Now, as we saw, we can use some properties of row and column operations to make our determinants easier. So I noticed that I have a factor of e to the x in everything in this column and a factor of e to the x in everything in that column. So I could write this as e to the x times 1 and 1 and also times by e to the x and times by x and x plus 1. So we would then get our determinant here. So this would be e to the x times e to the x, which is e to the 2x. And then to do the determinant of a 2 by 2 matrix, it's rather easy. We take EAD minus BC. So we'll have 1 times x plus 1 minus x times 1, which is e to the 2x times x plus 1 minus x, which is just a simple 1. So our determinant would be e to the 2x. And again, we call this the Wronskian of those two guys. And notice that our Wronskian is in fact a function. And this function is never 0. And so he's not identically equal to 0. So it's okay for the Wronskian to sometimes have some x values that make him be 0. But if he has any x value that make the Wronskian not be 0, then we can say that e to the x and x e to the x are linearly independent. Okay. Now, another thing that we want to talk about is solving a system using Cramers Rule, and we'll look at a 2 by 2 system here. So let's say that we have the ax plus by equals p and cx plus dy equals q system. Cramer found out that if we can do a times d minus b times c and find the determinant, and if that determinant is not 0, then the solution to this is x equals the determinant of p, q in the first column. So we put the constants in the first column, and then b and d, and we divide that by the determinant of the original coefficient matrix, a, b, c, and d. And similarly, we could find out what the y solution is by slapping the p and q in for the b and d, and then doing the determinant of that guy over the determinant of the original coefficient matrix. To see how this works, I had my calculator randomly generate some numbers. And so I've got negative 1x plus 8y equals 4, and negative 6x plus 9y equals 2. And if we wanted to solve that, let's do that using Cramer's method or Cramer's rule. So let's go ahead and find some determinants. So if we take a look at negative 1, 8, negative 6, and 9, so we'll have negative 9 minus a negative 48. So that's going to be, what's that going to be? 39. Okay. And if we take and put these constants in place of the coefficients of the x's, we're going to get 4 and 2, 8 and 9. And if we do that determinant, we're going to get 36 minus 16, which is 20. If we do it the other way, and we put the constants in for the coefficients of the y, our determinant will be negative 9 minus, I just put those in the wrong spot. So, whoops. So 4 and 2 in place of the y. So we're going to have negative 8 minus, I'm sorry, I screwed up. So let me rewrite that over here. Negative 1, negative 6, and 4, 2. So we'll have negative 2 minus negative 24, which works out to be 22. Therefore, the solution to this system would be y equals this guy, where we substituted the constants in for the coefficients of the x's. So that should be 20 over the determinant of the original matrix, 39. And y solution will be his determinant matrix, so 22 over 39. And just as a quick check, I went ahead and ran it in my calculator, and you'll see that the solution is that x is 20/39 and y is 22/39, as we would have predicted. So that is Cramers rule, and we'll come back to him a little bit later today. The other thing that I need to mention is when to use variation of parameters versus when to use the method of undetermined coefficients from the previous part of this section. So to talk about that, let's go ahead and look at some examples. In one of our examples from 5.5a, we had a non-homogeneous part, which was like e to the x plus 4x squared. And we had y triple prime plus y double prime is equal to that. Now, if we take a look at this guy and take his derivatives, we get e to the x plus 8x and e to the x plus 8. And so we can see that if we keep going with our derivatives here, it's going to be not too bad. So taking these guys and his derivatives, it's going to be something times e to the x plus something times x squared plus something times x plus something else, some other constant, okay? And so that's doable and manageable. But what if we have a non-homogeneous case where our non-homogeneous piece is something like e to the x over x squared plus 1? So when we take this guy, and let me give him a name, we'll call him f of x. If I take and find f prime of x, we're going to need the quotient rule, which will tell me to do x squared plus 1 times e to the x minus e to the x times 2x over x squared plus 1, quantity squared on the bottom. I can factor out an e to the x on the top, getting x squared minus 2x plus 1 over x squared plus 1 quantity squared. And that is harder and more difficult than the original. And then if we even do the second derivative, things get even worse. So we'll have x squared plus 1 squared times, and now we'll need the product rule inside the numerator, e to the x times 2x minus 2 plus e to the x times x squared minus 2x plus 1 minus e to the x times x squared minus 2x plus 1 times the derivative of the denominator, which would be 2 times x squared plus 1 to the first power times the derivative of the inside function because of the chain rule, which is 2x, all over x squared plus 1 squared squared would be to the fourth. And you can see that this is going to get really hairy really fast. So unlike the situations where we had these guys and the non-homogeneous piece and his derivatives were manageable, in situations like this where the derivatives get out of hand, we want to use another method other than the undetermined coefficients. It's true that you could do a little bit of simplification here, but you can see that this is going to get worse and worse and worse. And if this were like a third order, this is just going to get hideous. So that's where the method of variation of parameters comes in. And we'll pick up with an example with that in the next video.